Hello friends, today we are going to study Rolle's theorem. We will see what is the definition of Rolle's theorem. After that we will see what is graphically meaning Rolle's theorem, graphically what it is talking about. Let us understand what is the definition of Rolle's theorem is talking about. Rolle's theorem. Let A is a map from closed interval AB, like domain we are talking about closed interval AB to R or range is R such that f is satisfies these three properties. What are the three properties? First property is f is continuous. Just look at the interval. Continuous in closed interval AB means whole domain, and f is differentiable in open interval AB. That means we lifting the boundary, like we are not caring about in boundary it is differentiable or not. We are not caring about. Then f of a is equal to f of b. What do you mean by f of a is equal to f of b? The value of a function in the end point equal. Like f of x at point x is equal to a is equal to f of x at point x is equal to b. Like in the domain, from the domain you can see domain is our closed interval. At the end point functional value is the same. If these three condition is satisfied by a function f defined on closed interval AB to R, then this thing happen. What is talking about? Then there exists at least, this is important, there exists at least one point C belongs to open interval AB such that f dash C is equal to 0. There exists at least one point C belongs to open interval AB such that f dash C is equal to 0. Now let's understand like each point separately what it exactly mean as well as in graphical manner. First point is f is defined on closed interval AB. That means suppose any function we are defined on closed interval AB. Suppose this is our A, this is our B. Our domain is closed interval AB. Like we are concerned about this region, this closed interval AB for whole R. This is our domain and the range is whole R. Okay. Then function is continuous in closed interval AB. Like in this closed interval, we are talking about our function f of x is continuous. What do you mean by continuous? Like there is no gap in the curve of the function if we plot in the interval closed interval AB, right? Like this is our function which is continuous on closed interval AB. Also this we can plot like this is our graph. Also this is our graph. Also this is our graph. Any continuous graph between closed interval AB. This is talking about. Second point is talking about differentiable in open interval AB. What do you mean by differentiable in the open interval AB? This is our domain. This is A. This is B. We are concerned about open interval AB. Like we are concerned about differentiable in the open interval AB. A point is not included. This means for differentiability we are not including this point. We are not concerned about this point. Okay. Now, what do you mean by differentiable in graphically? That means there is no sharp edge. Continuous, the graph is continuous as well as there is no sharp edge. In this open interval AB, right, we are concerned about. Like the graph is not like that. This is not at this point. Like there is a sharp edge, right? So it is not differentiable at this point. So the Rolle's theorem needed what it is needed differentiable in the open interval AB. There is no sharp edge in the open interval AB. Also, this type of graph is not possible. Like it is concerned about. This is not requirement of the Rolle's theorem. The graph should be continuous, like this. The important thing is we can take like this. If it is not differentiable in the end point, it is also like acceptable. in the Rolle's theorem, as per the Rolle's theorem hypothesis. Suppose the graph is like that. Clearly, you can see there is a sharp corner this point, right? A. Similarly, this sharp corner is at point B. So if this is your function, okay, it is not differentiable at A and B. But this our requirement of how our hypothesis of Rolle's theorem is satisfied. Like it is differentiable in the open interval A B and as well as continuous in the closed interval A B. What is needed, right? So you understand what is the second point talking about. Now understand what is the third point talking about. I'm talking about the value of function at the end point is equal. Like here, let's observe what is the coordinate of this point. This is our a comma f of a. This coordinate our b comma f of b. Clearly, f of a is equal to f of b. It's understood, right? F of a, this side is same. Here, this side and this side. So, this is what our requirement in the third point. The functional value at the end point equal. Let's check what is the conclusion is talking about. If these three things happen, like this is our hypothesis, function is continuous in closed interval AB, function is differentiable in open interval AB, then at the end point functional value same, then what happens? There exists at least one point C belongs to open interval AB such that f dash C is equal to 0. Let's understand what do you mean by f dash C is equal to 0. If derivative is 0 at a point, then what do you mean by that? F dash C, that means f dash x when x is equal to C, right? Let's understand what is meaning of f dash x geometrically. So this is our graph. Let us suppose this is our f of x is a function like that. This is our f of x, and this is any point alpha. If suppose we are plotting the tangent at point alpha, then how it looks like? This is your tangent. This is a tangent touching at exactly one point. Suppose it making the x-axis, this is y-axis, an angle theta with x-axis. Then, if you want to find f dash x at C, then what is geometrically meaning? F dash C is equal to tan theta. That is slope of the tangent at x is equal to C. Slope of the tangent at x is equal to C, where theta is the angle between the tangent in anti-clockwise sense with the x-axis. So here what is requirement like in our Rolle's theorem, in the conclusion what it's talking about, f dash C is equal to 0, right? That means f dash C is equal to 0. Suppose in the cell like C is any point between open interval AB, right? Where it is C belongs to open interval AB. Suppose our theta is the angle of the tangent at point C in the open interval AB. Suppose this is we are taking out A, this is our B, and Suppose this is C. So at the point C we are producing the tangent. This is the theta. So what do you mean by that? F dash C nothing but tan theta is equal to 0. What it gives? Theta is equal to 0 degree. Theta is equal to 0 degree. What is meaning of theta is equal to 0 degree? That means like if this angle, let me change the color. If this theta becomes 0 degree, then how it looks like? Like C A B, then theta is equal to 0. That means the angle made by the tangent at point C is parallel to x-axis. Is parallel to x-axis. Graphically, you can come like it is clear. The tangent at point C is parallel to x-axis, right? That is meaning of theta is equal to 0. What is they? Let's understand. What the theorem exactly talking about? If any function f defined in closed interval b to r and satisfy these three conditions, then there exists a tangent which is parallel to x-axis and the corresponding x coordinate is lies in the open interval AB. The corresponding x coordinate lies in the open interval AB. Right? From the graph, let's together understand like what exactly the theorem talking about, including all the hypotheses and conclusion. This is our interval A, B, this is x-axis, this is y-axis. Suppose this is our chord, okay. Clearly, function is continuous in closed interval AB and differentiable in the open interval AB. Then what the theorem talking about? If f of A is equal to f of B, so this is your f of A, this is your f of B. If f of A is equal to f of B, then suppose we are trying to plot tangent at in the domain closed interval AB corresponding x coordinate. Tangent at this point, how do you do it? Like this, right? Similarly, tangent at this point is this. Tangent at this point is this. So, as per the hypothesis, there exists at least one tangent which is parallel to x-axis and a corresponding x coordinate. So this is C, lies in the open interval AB. This is actually obvious, right? Like if the function continuous in the closed interval AB, differentiable open interval AB, at endpoint functional value same, then there exists a tangent which is parallel to x-axis. From the graph it is understood what is exactly it is talking about. Now the question is like why is it at least one? Is there exist like any case where more than one may exist? Maybe more than two, more than three. Is there any case where these three conditions satisfy and more than one CG exists? Let's observe maybe. Okay, here exactly one C exists, right? But in the question this you can say if there C is equal to 0. C is unique here, right? C is unique. Unique in the sense only one C, so that delta C equal to 0. Suppose graph is like this. A, this is your B. Okay. F of A is equal to F of B. Like if we plot tangent at this point, how it looks like this. If we plot tangent at this point, this. If we plot tangent at this point, this. Corresponding x coordinate is this is C1, C2, this is C3. Clearly, C1 not is equal to C2 not is equal to C3, but f dash C1 is equal to f dash C2 is equal to f dash C3 is equal to 0. So we can observe from this graph, this is our x axis, this is our y axis, there exists three unique tangents which is parallel to x axis. Our function is like the hypothesis of Rolle's theorem satisfy continuity, differentiability, and any point functional value the same. Then what we observe, there exists three tangents, right? Corresponding x coordinate are C1, C2, C3. They are unique. There exists, this is f dash C1 is equal to 0. This is f dash C2 is equal to 0. This is f dash C3 is equal to 0. That's what it is talking about. Our Rolle's theorem. At least one. Here only one. Here our exists three distinct such tangent, right? At three distinct point there exists tangent which is parallel to x axis. That's the reason we need at least. Not like that three. There might exist more than three also. Maybe countable infinite or uncountable maybe. This is our like what Rolle's theorem talking about. Now what we do? Like what if the function is not continuous? Is such tangent exist? If function is not differentiable, then if such tangent exists, if this condition also not satisfied, if such tangent exist, this is a hypothesis, right? Like the best way to learn any theorem is the key point is drop hypothesis one by one hypothesis and observe what happened. Like why this thing is needed. Let us suppose if function is not continuous, then what happened? F of x is not continuous in closed interval AB. We will observe everything graphically. Suppose we have a function f of x and the graphical representation of the function is looks like this. This is our A, this is your B, your B. F of A is equal to F of B. Suppose like at this point the function we are defining, this is suppose our alpha function is here. This is your F of alpha. Clearly at alpha f of x is not continuous at x is equal to alpha, so implies not continuous in closed interval AB. Then like here if we plot tangent at this point, this is your tangent. If we plot tangent at this point, this is your tangent. If we can't plot tangent at this point, right? This is your point. If we plot tangent at this point, then how? This is a point, single point, right? So in this case, there does not exist such C such that f dash C is equal to 0. Third, our observation that there does not exist such C belongs to open interval AB such that f dash C is equal to 0. This is our first observation. Second observation. Say sigma y. Suppose our graph looks like suppose we have a discontinuity at this point. Like at this point, we define the function is here. Suppose this is our alpha. Clearly, function is not continuous at alpha. Alpha belongs to open interval AB, so not continuous in the interval AB. Also, since not continuous, not differential, but f of a is equal to f of b over here. But clearly, if we plot tangent at this point, this tangent is parallel to x-axis. This tangent is parallel to x-axis. What happened here? Function is not continuous in the interval, but there exists a tangent which is parallel to x-axis. The corresponding C would be known as C. This is largely open interval AB, right? So there exists C belongs to open interval AB such that f dash C is equal to 0. So in this case, function is not continuous and such tangent does not exist. Such C does not exist, so that f dash C is equal to 0. In this case, function is not continuous, but such C exists. That means if function is not continuous, we can't conclude anything. So C exists or not, like there exists some tangent which is parallel to x-axis or not, we can't conclude. So continuous is important for our hypothesis. If we drop, we can't say anything. For the existence of the tangent, we can't, like through Rolle's theorem, as we talking about, we can't drop the continuity condition. Suppose function is not differential but continuous. Okay, see. Now in open interval. Similarly, observe by graph. Not differential means there is a sharp corner in the open interval AB. This is our x, this is our y. This is our interval. Here function is continuous and we are taking f of a equal to f of b. If f of a not equal to f, then fine. So we are taking just like that. Here we can see, suppose this coordinate is from alpha. At x is equal to alpha, f of x is not differentiable, right? And alpha is lies in open interval. So f of x is not differential in open interval. Also, if you plot tangent at this point, this is your tangent. But at x is equal to alpha function is not differentiable, right? So we can't plot tangent at this point. If we plot tangent, this may be tangent, this may be tangent, but it is not unique, so we can't plot tangent at this point. That means what it implies, there does not exist such C such that f dash C is equal to 0. That means there doesn't exist any tangent on the curve which is parallel to x axis. So let's observe second case. This is our y axis. Suppose this is our curve continuous, it is on our alpha. There is a sharp edge, right? Sharp edge at clearly at x is equal to alpha. F of x is not differentiable at x is equal to alpha, which is belongs to an interlevel. But observe the one important thing. Suppose we are plotting tangent at this point. This is how our tangent looks like. If I plot tangent at this point, how this looks like? This is our tangent. Similarly, if I plot tangent at this point, this is our tangent. So this is C1, this is C2. Clearly, there exists tangent at point C1, which is parallel to x axis. This two line are parallel line. Similarly, there exists C2 at there exists tangent at point C2, which is parallel to x axis. So what it implies? There exists C1 and C2 such that f dash C1 is equal to f dash C2 is equal to 0. Like from these two examples you can observe both case function is not differentiable, but in one case there exists tangent which is parallel to x axis, in other case there doesn't exist tangent. Here that doesn't exist, here exists. So if function is not differentiable, we can't conclude anything. Both are possible. So for the Rolle's theorem, differentiability is also most important. Now observe the third one. What if the functional value at the endpoint not equal? F of A is not equal to f of B. Suppose this is our A, this is our B, this is f of A, this is f of B. Clearly f of A not is equal to f of B. But if we plot tangent at this point, this is how it looks like. If we plot tangent at this point, how this looks like. If we plot tangent at this point, it looks like this. Clearly, there exists a tangent which is parallel to x axis, but f of A not is equal to f of B. So what it implies? There exists C belongs to opponent Rolle B such that f dash C is equal to 0. There exists tangent which is parallel to x axis. Second case. here also our function is continuously closed interval. Differentially open interval, right? We are not concerning about. End point may not differential. We are not concerning about with this. So clearly here also f of a is not equal to f of b. In this case, that does not exist of tangent, which is parallel to x axis. So C belongs to open interval b, such that f dash c is equal to 0. So if f of a not is equal to f of b, we can't conclude anything. Maybe there exists tangent which is parallel to x axis, may not be there exists tangent which is parallel to x axis. So we observe, like if function is not continuous, like here if f of a not equal to f of b, both cases may be possible. Maybe there exists a tangent, may not be there exists a tangent. So these three conditions are most important. Function should be continuous, function should be differentiable, function should at end point functional value should be same. Then we can conclude this thing. This hypothesis is most important. This is the important thing. Then there exists at least one c so that and in the open interval will be f dash is equal to 0. So this is all about the Rolle's theorem and the graphical meaning also. What is graphical meaning? We observe, like there exists if this thing satisfies, there exists a tangent which is parallel to x axis. This is the meaning by graphically. In the next class, we will see some entrance question and some application of the Rolle's theorem. Thank you for watching.